Hello students, this is Mr. Allen. We are going to continue our journey through chapter 7. We're actually going to skip over section 7.6 and go right to 7.7, which is something we actually cover in the AB curriculum, but we'll go a little bit deeper into it this year, and that is indeterminate forms, and something you're very familiar with, and that's L'Hopital's rule. So our objective here today is to recognize limits that produce indeterminate forms and to apply L'Hopital's rule to evaluate a limit. So the forms 0 divided by 0, infinity divided by infinity are called indeterminate forms because there's no guarantee that the limit exists, nor is there any way for you to indicate what the limit is if it does exist. In other words, literally it could be any possible value or it could be D and E. When you encounter one of these indeterminate forms, you attempted to rewrite the expression. So for example, if we look at this first limit at the bottom where it says the limit as x goes to -1 of 2x squared minus 2 over x plus 1. Well, if you factor out the numerator, it will cancel with the x plus 1 in the denominator. And so you get an equivalent form of 2 times the quantity x minus 1, which can be evaluated as x goes to -1, and you'll get -4. Similarly, and by the way, that was 0 over 0. Similarly, on the second example below, another algebraic example, you can go ahead and basically divide through by x squared, and then you can get the final answer there of 3/2. So there are ways to deal with these indeterminate forms algebraically, but not always. Here's another more interesting example involving the exponential function. And again, it's just factoring. And basically what we're doing is we're producing a curve that is identical to the original curve, except at one point, and that allows us to get the answer 2. That was kind of the big idea. In fact, when we talked about this in Calc AB, we talked about, curves that are equivalent, but at one point. So we basically remove that hole, and that allows you to calculate the limit. Now there's an assumption there that it's just a hole. However, not all indeterminate forms can be evaluated by algebraic manipulation. This is often true when both algebraic and transcendental functions are involved. So for example, if we look at the limit as x goes to 0 of e to the 2x minus 1 over x, the numerator involves a transcendental function e to the 2x, and the denominator involves the algebraic function x. Now, if we just did direct substitution, you will see that this ends up being 0 over 0, because what you're going to have is you're going to have e to the 2 times 0 minus 1 over 0. So you end up with 1 minus 1 over 0, which is 0 over 0. That's an indeterminate form. But if we rewrite this expression in such the way that we just basically break this numerator into 2 pieces with the common denominator of x, we end up with infinity minus infinity. So that doesn't really help us because, by the way, infinity minus infinity, I should note this, infinity minus infinity does not equal 0. It might equal 0, but in general, it does not. You could use technology to estimate the limit. And if you look carefully here, as we get closer to 0 from the left and closer to 0 from the right, you can probably guess that the answer here is 2. Well, the answer to do a problem like this is, of course, L'Hopital's rule. So if we go back to this example here, and if we do the derivative of the numerator, you'll get 2e to the 2x. The derivative of the denominator is 1, and we evaluate the limit as x goes to 0. Now we get 2 over 1, which of course is 2. And that's by L'Hopital's rule, which is here on this slide. I want to read it to you because I need you guys to have a better grasp of when to use it and when not to use it. So let functions f and g be differentiable on the open interval except for possibly at c. Assume that g prime isn't equal to 0 because we're not allowed to divide by 0. If the limit of f of x divided by g of x as x approaches c produces an indeterminate form of 0 over 0, then the limit of the quotient of the functions is equivalent to the limit of the derivatives of the functions. Provided this limit exists on the right, this result also applies to infinity over infinity, negative infinity divided by positive infinity divided by negative infinity, and negative infinity over negative infinity. So it applies to 0 over 0 and infinity over infinity in general. So let's look at this example a little bit more worked out. I'm going to go a little bit slower this time. So the first thing that we're going to do is, if we do direct substitution, we can see that the numerator's limit is 0, the denominator's limit is 0. Therefore, we have a 0 over 0, and that is an indeterminate form. Notice how I'm showing my work here. Notice that I'm splitting these two guys up. Now we can apply L'Hopital's rule, since we know we have 0 over 0. So we're going to do the derivative of the numerator and the derivative of the denominator. So that means that this limit is equivalent to this limit according to L'Hopital's rule. And of course, now we can just do that substitution to get the 2. So here I kind of spelled out the work a little bit more clearly. The forms 0 over 0, infinity over infinity, infinity minus infinity, 0 times infinity, 0 to 0, 1 to infinity, and infinity to 0 are all identified as indeterminate forms. They are similar forms that you should recognize as determinate. So these here can be determined. I'm telling you infinity plus infinity tends to infinity. Negative infinity plus infinity, negative infinity tends to negative infinity. 0 to the infinity is 0. Now notice up here I said that infinity to the 0 is indeterminate. And 0 to the negative infinity tends to be infinity. As a final comment, remember that L'Hopital's rule applies only to quotients leading with the indeterminate forms 0 over 0 or infinity divided by infinity. Let me show you an example of using L'Hopital's rule incorrectly. So let's say I want to find the limit of e to the x over x as x goes to 0. This is incorrect because here's what happens is students know L'Hopital's rule, so they automatically want to jump to that. They say, oh, that's a transcendental over a algebraic. So I'm going to do L'Hopital's rule. And so then we get the answer here of 1. This is actually incorrect though. And the reason it's incorrect is this. This is why we want to split these into 2. What is the limit as x goes to 0 of e to the x? Well, that's 1. What is the limit as x goes to 0 of x? Well, that's 0. So that's 1 over 0. This is not an example where we could use L'Hopital's rule. In fact, this limit is not something that we're going to say is just like, we wouldn't say it's just 1. And I'm just going to encourage you, look at your graphing calculator and see what it says. Okay. The reason this application, and I just went through all that. Okay, so let's go ahead and move forward. Last example I'm going to kind of do on my own here. So it says evaluate the limit as x goes to infinity of e to the negative x times the square root of x. So this doesn't maybe necessarily look like a quotient, but we could easily write it as a quotient. In fact, I hope you would agree that we could simply write this limit as x goes to infinity. In fact, let me ask you this. You may want to pause the video and see if you can figure out what this limit is. But I'm going to keep going because you may not want to do that. So I'm going to leave that square root of x in the numerator. Now the denominator, if I remember this is a negative exponent, I can move that into the denominator. Now watch what happens. If I take the numerator's limit, so that'd be the limit as x goes to infinity of the square root of x. Well, that's going to infinity. That's tending to infinity. If I do the same thing with the denominator, let's do that in green, let's say. The denominator, if we do the limit as x goes to infinity of e to the x, that also goes to infinity. So we have a case where we have infinity over infinity. So this is going to be a good example of when we're going to want to use L'Hopital's rule. So let's go ahead and do that. Let's do it in blue. So this limit, I'm going to write this again, the limit as x goes to infinity of the square root of x over e to the x is going to be equivalent to the limit as x goes to infinity. Now I got to do the derivative of the square root function. Remember, x to the the square root of x is the same thing as x to the 1/2, and that's going to give us 1 over 2 square roots of x for that guy. The denominator is just e to the x. Now we can go ahead and figure out what our answer is. The bottom is going to go to infinity. The numerator is going to go to 0. This is not an indeterminate form, so this limit is 0. And I think we'll end it there. Thank you for your attention.